Hello everyone. So, in today's class, first we will use momentum integral equation which we derived for laminar flows, and we will find the friction coefficient for turbulent flows for flow over flat plate, and then we will find the heat transfer coefficient and Nusselt number for flow over flat plate. So, we can write the momentum integral equation which we derived for the laminar flows. So, this is your d of dx 0 to delta 1 minus u by u infinity dy is equal to nu by u infinity square del u by del y at y is equal to 0, and this you can write in terms of the wall shear stress tau w by rho u infinity square. Okay. So, this equation also can be used for time average velocities, okay, in turbulent flows. So, you just replace u is equal to u bar. Okay. So, if you replace u is equal to u bar, then this momentum integral equation we can use for these turbulent flows. Now, you know that to use this integral equation, we need to find or we need to assume some velocity profile. In turbulent flows, it is very difficult to assume the velocity profile. So, Prandtl and von Karman, what they did, they used very crude and simple method, but it gives very accurate result for flow over flat plate or for external flows. So, they used the solution of Blasius for circular pipe case, and that they used the velocity profile for the flow over flat plate. So, you can see Prandtl and von Karman used the model from Blasius model, which was developed for the shear at the wall of a circular pipe. Okay. So, Blasius proposed for circular pipe based on the dimensional analysis and experimental data, this CF as 0.0791 RED to the power minus 1 by 4, and it is valid in the range of Reynolds number based on diameter 4000 less than equal to RED less than equal to 10 to the power 5. So, this is for internal flows, okay, pipe flow, where CF is defined as tau w by half rho um square, where um is your mean velocity. Okay. So, based on this empirical relation, your Prandtl and von Karman developed the velocity profile inside a pipe as, so Prandtl and von Karman showed the velocity profile in the pipe u bar by UCL is equal to y by R0 to the power 1 by 7. In this relation, y is measured from the pipe wall and UCL is your center line velocity, okay, and R0 is the radius of the pipe. So, Prandtl and von Karman actually using this relation, they use the velocity profile for flow over flat plate, just putting the R naught as delta, okay, that is your boundary layer thickness, and UCL in this case there is no central line velocity. So, UCL is substituted with the free stream velocity u infinity. So, we will use for flow over flat plate this velocity profile u by u infinity. So, UCL is actually replaced with u infinity equal to y by delta, where r naught is replaced with delta boundary layer thickness to the power 1 by 7. So, you can see that it is a well known 1/7 law of velocity profile, okay, 1/7 law of velocity profile. So, although they propose the velocity profile for the flow over flat plate like this, but it has some fundamental problem. So, if you calculate the shear stress at the wall, it will become almost infinity. Okay. So, to avoid this problem, they used the correlation for the CF from the pipe flow relation. To avoid this problem, Prandtl and von Karman adapted Blasius correlation to find an expression for the wall shear stress on a flat plate. Okay, so, they use tau w by rho um square. So, this is for pipe flow 0.03326 divided by nu by r naught um to the power 1 by 4. So, now you can substitute UCL as u infinity and r naught as delta, but the mean velocity um, okay. So, by UCL it can be found for 1/7 law velocity profile inside a pipe as by UCL is equal to 0.8167. So, these are valid for pipe flow. So, now you can use UCL, you can substitute with u infinity, okay, and r naught you can substitute with delta. Okay. So, now if you substitute, then you will get the shear stress relation for flow over flat plate. Okay, you can use now CF by 2, which is your tau w by rho u infinity square. After putting all these values, you can rearrange and you will get as 0.02333 nu by u infinity delta to the power 1 by 4. So, you can see for flow over flat plate, this CF by 2 is given in terms of the boundary layer thickness delta. Okay, this is the CF by 2. Now, we can use the momentum integral equation and we can substitute the velocity profile 1/7 law velocity profile and this shear stress relation, and we can find what is the boundary layer thickness. So, we have the momentum integral equation as d by dx 0 to delta 1 minus u bar by u infinity into u bar by u infinity dy is equal to tau w by rho u infinity square. So, now we have u bar by u infinity, okay. Prandtl and von Karman proposed as y by delta to the power 1 by 7, and you have tau w by rho infinity square is equal to 0.02333 nu by u infinity delta to the power 1 by 4. Now, you substitute these two in the momentum integral equation and find the value of delta, and once you know the value of delta you will be able to find the skin friction coefficient, because in the skin friction coefficient you have the unknown parameter delta. So, if you substitute it you will get d of dx 0 to delta. Okay. So, if you multiply u bar by u infinity, then you will get here y by delta to the power 1 by 7. So, minus, you can see u bar by u infinity whole square you will get. So, it will be y by delta to the power 2 by 7 dy is equal to, now substitute this tau w by rho infinity square here. So, 0.02333 nu by u infinity delta to the power 1 by 4. So, if you integrate it, what you will get dy by dx. So, you can see it is y to the power 1 by 7, and in the denominator you will have 1 by 7 plus 1. So, it will be 8 by 7. So, you will get finally 7 by 8 delta to the power 8 by 7 by delta to the power 1 by 7 minus here 2 by 7. So, in the denominator you will have 2 by 7 plus 1. So, that means it will get 7 by 9 delta to the power 9 by 7 to the power delta to the power 2 by 7. Okay, and in the right hand side you will have 0.02333 nu by u infinity delta to the power 1 by 4. So, this if you do the algebra you will get 7 by 72 d delta by dx is equal to 0.02333 nu by u infinity delta to the power 1 by 4. Okay. So, this delta you take in the left hand side. So, you will get delta to the power 1 by 4 d delta, and this if you take in the right hand side. So, you will get 0.02333 into 72 by 7, okay, and nu by u infinity to the power 1 by 4 dx. Okay. So, now if you integrate it, you see nu u infinity are constant. Okay. So, you can integrate this. So, you will get 4 by 5 delta to the power 5 by 4 is equal to 0.02337 into 72 by 7 into nu by u infinity to the power 1 by 4 x plus c. Okay. So, we will assume here that you have the turbulent flow from the leading edge of the flat plate. Okay. So, first Prandtl proposed this assumption so that we can use the condition at x equal to 0, that means at the leading edge of the flat plate you have boundary layer thickness delta 0. So, this is the assumptions you have to take. Okay. So, if you take these assumptions, then you can use the boundary condition at x equal to 0, delta is equal to 0. So, we are assuming that you have a turbulent flow over this flat plate starting from the leading edge. So, we are assuming the entire flow along the plate as being turbulent. Beginning from the leading edge. Okay. So, this assumption was first proposed by Prandtl. So, if you assume this, then you can put at x equal to 0, delta is equal to 0. So, that means your constant c will be 0. So, if you put c is equal to 0 and if you rearrange it, you will get delta which is function of x as 0.3816 u infinity x by nu to the power minus 1 by 5 x. Okay. So, you can write delta by x is equal to 0.3816 Rex to the power minus 1 by 5. Okay. So, here you can see that your boundary layer thickness varies as x to the power minus 4 by 5. Okay. So, your in this case you can see that your boundary layer thickness delta varies with x to the power 4 by 5. So, delta varies as x to the power 4 by 5 for turbulent flows. Okay. For laminar flows, do you remember what was the delta? So, it was 5 by root Rex. So, that means delta by x was 5 by root Rex. Okay. So, that means delta varies as x to the power half, okay, for laminar flows. Okay. And now, if you find the CF, okay, so now we can find CF, because in the CF we have unknown parameter delta. So, you can substitute it here. CF by 2 is equal to tau w by rho u infinity square is equal to 0.02333 nu by u infinity delta to the power 1 by 4. So, you substitute here this delta value. Okay. So, if you substitute it, you will get CF by 2 is equal to 0.0233. Now, you have nu by u infinity. So, here you put x. So, you will get x by delta, and x by delta you can put as, or in the denominator delta by x you can put as 3816 Rex to the power minus 1 by 5 to the power 1 by 4. Okay. So, if you rearrange it, you can write as CF by 2 is equal to, so here u infinity x by nu, again you will get 1 by Rex. So, here Rex to the power minus 1 by 5 is there. So, this you can write as 0.02968 divided by Rex to the power 1 by 5. Okay. So, now CF is known. Okay. And for laminar flow, you know CF varies as Rex to the power minus half, and in turbulent flows you can see CF varies as Rex to the power minus 1 by 5, okay, for turbulent flows. So, now whatever expression we have derived for this CF by 2, that we will use to find the heat transfer coefficient. Okay. So, you can see we have already derived these for fully turbulent boundary layer u plus is equal to 1 by kappa ln y plus b. Okay. And T plus also we have derived Prandtl number T by kappa ln y plus by y1 plus Prandtl number y1 plus. So, 1 plus this you need to find for different types of fluid. Now, u tau you know is defined as root tau w by rho. So, now if you define u bar by u tau, okay, so you can see this will become root 2 by Cfx. Okay. So, this you can show. Okay. So, now u by u tau is this. So, here you can see u plus is nothing but u bar by u tau. So, this is your u bar by u tau, and y plus is equal to y u tau by nu, okay, plus the constant b. So, at y is equal to delta, at the edge of the boundary layer you have free stream velocity u infinity. So, u bar by u tau, now this u bar you can substitute u infinity. So, u infinity by u tau is equal to 1 by kappa ln delta u tau by nu plus b. So, this is we have derived. Now, if you see here, here we will assume that delta is order of delta t, okay. Delta is order of delta t, so that our derivation will be simplified. So, with that we know that at the edge of the boundary layer we have t bar is equal to t infinity. So, here if you put t bar is equal to t infinity, so this you can write t w minus t infinity rho Cp u tau by q double prime w is equal to Prandtl number t by kappa ln. Now, y is delta u tau by nu divided by y1 plus Prandtl number y1 plus. So, after substituting t plus value, just we have derived at y is equal to delta. Okay. So, now these two relations we have. Now, what you do, you see in both the equations you have delta u tau by nu, okay, delta u tau by nu. Now, eliminate delta u tau by nu and put u bar by u tau is equal to root 2 by Cfx. Okay. So, if you do that, then you will get h by rho Cp u infinity is equal to Cfx by 2 divided by this expression. Okay. So, now we will define Stanton number. Already we have discussed about this. So, Stanton number you can write as Nusselt number divided by Reynolds number Prandtl number. So, Stanton number x is nothing but h by rho Cp u infinity. So, this if you put, then now we will be able to find what is the heat transfer coefficient, and from there we will be able to find what is the Nusselt number. So, now we have just expressed Stanton number with this. Now, we will assume turbulent Prandtl number as 0.9, y1 plus as 13.2 and the constant b as 5.1. So, these are from empirical values, okay. From the experiments these values are found. Now, if you put all these here, then you will get Nusselt number x by Reynolds number x Prandtl number is equal to Cfx by 2, and if you put all these values you are getting 0.9 plus Cfx by 2 to the power half into 13.2 Prandtl number minus 10.25. Okay. So, you can see from this expression now you will be able to find what is the Nusselt number or also heat transfer coefficient. Now, this we have derived using the two layers model, because we have used for fully turbulent flows what is the u plus and t plus expression, and from there we have derived the expression for Nusselt number here. You can also use Colburn analogy. So, that already we have discussed. So, the Colburn analogy is considered to yield acceptable results for including the laminar flow regime and Prandtl number ranging from about 0.5 to 60. Okay. So, this Colburn analogy if you use, so you know that Stanton number Prandtl number to the power 2 by 3 is equal to Cfx by 2, okay, and Stanton number now you substitute Nusselt number x by Rex Prandtl number, and from the integral solution, okay, just in this class we have derived Cfx by 2 is equal to 0.0296 Rex to the power minus 1 by 5. So, you can see in the Colburn analogy we will use this integral solution of Cfx by 2, and if you put it here and if you find what is the Nusselt number, you will get Nusselt number x in terms of Reynolds number and Prandtl number. So, you can see Nusselt number x is equal to 0.0296 Rex to the power 4 by 5 Prandtl number to the power 1 by 3. So, this is from Colburn analogy, just using the integral solution from integral solution of Cfx by 2 you can find the Nusselt number. This is your local Nusselt number, and it is valid for Prandtl number greater than equal to 0.5. Okay. And if you find the average Nusselt number, just integrating from 0 to L, you will get average Nusselt number as 0.037 REL to the power 4 by 5 Prandtl number to the power 1 by 3. So, this actually gives a reasonable good results. Okay. This is simple simplified expression, but you can also use this expression as well. So, now if you have laminar region in the beginning, then you have turbulent region. Okay. And you know that critical Reynolds number is your 10 to the power 5. So, in this region if you find the what is the average Nusselt number, okay, considering both laminar and turbulent regime, that now we will find. So, determine the average Nusselt number for heat transfer along a flat plate of length L with constant surface temperature. Use White's model for turbulent friction factor and assume a laminar region exists along the initial portion of the plate. Okay. So, if you consider a flat plate, okay, so we are considering that initial region you have laminar flow, okay, and then you have turbulent. Okay, so if you see the, so this is your boundary layer thickness and this is your y, this is your x. Now we will use White's model. So if you see what is White's model, White's model, we have found Cf by 2 is equal to 0.0135 divided by Rex to the power 1 by 7. Okay. And from Colburn analogy, and you can find the Nusselt number in turbulent flow regime. So, Stanton number x, Prandtl number to the power 2 by 3 is equal to Cf by 2 is equal to 0.0135 divided by Rex to the power 1 by 7. Okay. So, Stanton number x, you know, it is Nusselt number x divided by Reynolds number into Prandtl number, and your Prandtl number to the power 2 by 3 is equal to 0.0135 divided by Rex to the power 1 by 7. Okay. So, Nusselt number you can find, okay, for turbulent flows as 0.0135, Prandtl number to the power 1 by 3 and Rex to the power 6 by 7. Okay. So, using White's model we found the Nusselt number in the turbulent region as this. Okay. And you know, for laminar region, okay, we have already derived this Nusselt number, this is a local Nusselt number in laminar region as 0.332, Prandtl number to the power 1 by 3 and Rex to the power half. Okay. So, this we will use and we will find the average heat transfer coefficient for both laminar and turbulent regime. So, how do you calculate average Nusselt number? Average Nusselt number we calculate as okay, H bar L is equal to 1 by L 0 to L H, which is function of x dx. Okay. And now Nusselt number x we know as Hx by k. Okay. So, you can find H is equal to Nusselt number x k by x. Okay. You substitute it here. So, you will get 1 by L, okay, k is constant. So, you can take it outside. Okay. So, you will get 0 to L Nusselt number x by x dx. Okay. Now, if you find the Nusselt number, average Nusselt number, if you find the average Nusselt number, now it will be H bar L L by k. Okay. So, you can simply see this will be 0 to L Nusselt number x by x dx. Okay. Now, considering the laminar and turbulent region, for laminar and turbulent region, okay. So, Nusselt number, average Nusselt number, so it will be 0 to xc, okay, up to which laminar flow exists. So, it will be 1 by x Nusselt number x laminar dx plus, now from xc to L 1 by x Nusselt number x turbulent dx. So, we have already found the expression that you substitute here. So, you will get 0 to xc, if you rearrange you will get 0.332 Prandtl number to the power 1 by 3 u infinity by nu to the power half x to the power minus half dx. Okay. And in turbulent region you will get xc to L 0.0135 Prandtl number to the power 1 by 3 u infinity by nu to the power 6 by 7 x to the power minus 1 by 7 dx. Okay. So, if you perform the integration you will get 0.664 Prandtl number to the power 1 by 3 Re based on xc, okay, because you are integrating 0 to xc. So, you will get Re xc half plus 7 by 6 into 0.0135 Prandtl number to the power 1 by 3 into Rel to the power 6 by 7 minus Re based on xc, you will get 6 by 7. The critical Reynolds number, if you consider 5 into 10 to the power 5, then you will get, so this is if you consider 5 into 10 to the power 5 and substitute it here, and you will get average Nusselt number as 0.0158 Rel to the power 6 by 7 minus 739 Prandtl number to the power 1 by, okay. And if you neglect the laminar length, if laminar length had been neglected, the resulting correlation would be Nusselt number L is equal to 0.0158 Rel to the power 6 by 7 Prandtl number to the power 1 by 3. So, it is for fully turbulent flow, considering the turbulent flow from the beginning of the flat plate. Okay. So, in today's class we started with the momentum integral equation, which we derived for laminar flows, and we substituted u as time average velocity u bar. From there with the correlation of pipe flow, we could find the velocity distribution u bar by u infinity as y by delta to the power 1 by 7. So, this is known as 1/7 velocity profile. And also we saw that the problem is finding the tau w, because if you use this velocity profile as wall y is equal to 0, you will get infinite shear stress. So, to avoid that, again from Blasius relation of CF, we used the turbulent friction factor for the flow over flat plate. Now, that we expressed in terms of the unknown parameter boundary layer thickness delta. Now, we substituted this velocity profile as well as the turbulent friction factor in the momentum integral equation, and we found the value of turbulent boundary layer thickness delta. And once you know the delta, so we could find the value of Cfx. Then using the relation for fully turbulent layer, this u plus and t plus values, we found using the Colburn analogy the expression for Nusselt number. And also for using this integral solution, whatever we found the value of Cfx, that we used the Colburn analogy, and we found the simplified expression for the Nusselt number, local Nusselt number as well as the average Nusselt number. Thank you.